Okay, so today we are doing 5.3, which is logarithmic functions and graphs. Previously in 5.2, we talked about exponential functions and graphs. Here's the nice thing about exponential functions and logarithmic functions that we're going to see in just a minute, is that they're actually inverses of each other. And so that's really nice because a lot of times we're going to use one or the other to describe it. So we're going to play with logarithms, but then we're going to talk about them with exponents, and so we're going to go back and forth. So this section gives you a lot of extra practice from the previous section and vice versa. So a logarithmic function states that for x is greater than 0, so x has to be positive, and b is greater than 0, and b is not equal to 1, then we have y equals the log base b of x is equivalent to b to the y equals x. So when you look at a logarithmic equation or function, you have this little b down here next to your log, and that means that's your base. And they use b as the letter to help you connect it to the base. And then you have what you're taking the log of is actually the x in this case. And so if we're thinking about it as a function, then we use the f of x notation instead of the y. And this means the logarithmic function with the base of b. But as you can see, we use our exponential to actually describe or define our logarithmic, because we say that our logarithmic is equivalent to b raised to the y of x. And so we actually have a lot of the same components in our logarithm that we have in our exponential. They just look slightly different. In our logarithm, we do have a base. That's that lower b. Just like in our exponential, we have a base. That's what the big number is that supports your exponent. In your exponent, you obviously have an exponent. That's our y. And then in our logarithm, the equivalent is, again, the y, which is the exponent. And so you're going to hear me today and a lot more times as we move forward in this chapter say these next few words. The base becomes the base, and the answer becomes the exponent. You're going to hear me say that over and over and over again. Because as we go from logarithms into exponentials, that's what we're doing. The base of our logarithm becomes the base of our exponent. The answer of our logarithm becomes the exponent. And then what you were taking the log of becomes your new answer. That one doesn't really go with the base becomes the base, the answer becomes the exponent. It doesn't seem to flow as well, but that's what else happens. So base becomes the base, answer becomes the exponent. And then the second star says the inverse of your exponential is your logarithm. And the flip of that would also be true. The inverse of your logarithm is your exponential. And remember from previous sections that when you are inverses of each other, what happens is we flip our x's and our y values. So if you can graph the exponential equation, then you can graph the inverse simply by switching your x's and your y's. And that's actually how we're going to do a lot of our graphing. Because if you look at your calculator, you type in on your calculator different values and logarithms, you're going to get all these really gross decimals. And I don't know about you, but I don't like graphing with decimals because that's not nice. It doesn't fit nice on our grid. And so a lot of times what we're going to end up doing is we're going to convert our logarithms into exponentials and graph that, and then we can switch the x's and the y's around to get a nice logarithmic graph out of it. Try some? Yeah, we are. We're just going to start with going back and forth between our logarithms and our exponential forms. We are not solving. We are not finding out what x is. We are not evaluating. Those are words you need to look for in your problems. Evaluate, solve, those kinds of words. This simply states write in exponential form. That's it. So that's all we're going to do. We're not going to figure out what x is or b or y. We're just going to switch back and forth between the two different forms. So if we look at that first one, where we're going to write it in exponential form, it says 2 equals log base 5 of x. And this is where we're going to use that base becomes the base and the answer becomes the exponent. So what is the base of this logarithmic equation? 5. So that becomes the base of our exponential. Base becomes the base, and then our answer of our logarithm, which is 2, becomes the exponent in our exponential. And what we were taking the log of, which in this case is just x, becomes our new answer. Hopefully at that point you can see it's very quick and easy to solve then either that logarithm or that exponential at this point, because 5 squared is 25. But it does not ask us for that. It just says write it as an exponential, so that is where we would stop. What would b be? Yep. b to the third equals 64. The base becomes the base, our answer becomes our exponent, and what we took the log of will become our new answer. Questions? Okay. So the last one then will become what? Three raised to the y equals 7. Base becomes the base, the answer becomes our exponent, and what we were taking the log of becomes our new answer. Exactly right. Questions on how we go from logs to exponentials? Okay. If we're going the opposite direction, where we go from exponentials to logs, it's still very similar. We're just kind of thinking of it backwards. The base still becomes the base. So the base of our exponential will become the base of our logarithm. So we're going to have log base 12 of something equals something. Now the answer of our log is the exponent of our exponential. So over here then I'm going to have a 2, and the only thing left then is the answer of our exponential is what we were taking the log of. So sometimes it's nice, or it's easier to write out like log, and then you leave a blank for the base and a blank for what you're taking the log of equals, and you have your answer, and you kind of fill in those 3 different spots. And you can always check yourself by going backwards. Like on that first one, I can say the base becomes the base, so 12 becomes the base. My answer becomes the exponent. Do I get back over here to the exponential that they gave me? And I do. So what would be the logarithmic form for b, where we have b to the third equals 8? That's going to be log base what? B. Log base b of what? 8. Equals what? Yeah. The base becomes the base, my answer became the exponent. Or my base became the base, and my exponent became my answer, and then my answer becomes the new log. So the last one then, if my base of my exponent becomes the base of my log, the answer of my exponent becomes what I was taking the log of, and my exponential becomes, or my exponent becomes my new answer. Now, some of you who have played around with logs or remember anything about logs, this one might set off some red flags for you, and that's okay. It should, because there is a special kind of log when it has a base of e. That's known as our natural log. We mentioned very slightly at the end of 5.2 that there is this number in math, and it's called e, and it's 2.15 or 5.1. It's kind of like pi in that it's this irrational number. And we deal with it mostly in terms of our logarithms. And there's a special logarithm that has a base of e like this, and we call this our natural log. And that's what we're going to see right here. There's some special log rules. Log base E, we usually represent that as ln. That's not a 1n, that's an ln. And that means natural log. If you have a log that doesn't have a base written next to it, we understand that to be log base 10. That's our common log. So those are the two different kind of scenarios you're going to have. I guess there's three. Because you have logs where you have the bases written and represented by another number that's not 10 or E. If you have log written like this, where there is no base written, it's log base 10, or the common log. And if you have ln written, then it's understood that that's the same thing as log base E. Now, some of the other important rules is if you have log base A of 1 equals 0. The reason for that, like this first rule up here, is if I write this in exponential form, this log base A of 1 equals 0, my base becomes my base and my answer becomes my exponent. Well, what is anything to the 0th power? 1. So when you take log of 1, regardless of what base you have, you will always get 0. And that's why over here, with the ln of 1, we also get 0. The next rule is log base A of A equals 1. Again, this is more noticeable as to why if you convert it over to your exponential, because your base becomes the base and your answer becomes your exponent. Anything to the first power is going to stay the same. So if you have the base the same as what you're taking the log of, you always get the same thing out over here. So base in this, if these two numbers are the same, it always equals 1. That's why over here, ln of E also equals 1. Because ln of E is the same thing as log of E, log base E of E. If these two numbers are the same, you will always get 1. Always, always. And when I go throughout my notes, I usually write my ln with a cursive L like that to make it more noticeable that it's not a 1. Just so you know. So those are very important rules that you're going to use a lot as we move forward in this section and start simplifying things, but also as we start solving our exponential and logarithmic equations later on. So this is a very good little section to kind of memorize. Are there questions about any of those rules?
And you may have already mentioned this, but what are the ends representing on log A1?
Which one? Sorry, start over.
The top two.
This?
The ends.
The ends. This?
Is that not an end? Yeah.
This over here is ln of 1.
What does the end mean?
Natural.
Oh, okay.
It's natural log, but because it's flip-flopped, because it's, I'm sure it's Latin.
Oh.
So this looks, right here, this looks like the absolute value of n. It means ln of 1. Which again, if I switch this from ln or from logs over into exponentials, my base is e for a natural log. So base becomes the base, my answer becomes the exponent. E to the 0th power is 1. Other questions? Okay. Some of your problems had calculators. I don't like calculators. But just so you know how to use your calculator to compute logs, which my calculator is a little bit different than yours. Mine is one you can't use, but it is a TI, so it is very similar. In your calculator, you probably have a log, like an LOG button or an LN button. Even on cell phones, if we turn our cell phones the opposite way, it'll allow us to do logs. Like if you have an iPhone, if you turn it this way, you get like a scientific calculator. and you have an ln button, and you have a common log button. And I don't see another log button. And that's because you can't do another log button, and we're going to see that later. Any base besides e and 10, your calculators will not compute for you. They won't. And at the end of class, we're going to learn a change of base formula that allows us to actually compute those using our calculator. And if you look at all these examples right here using a calculator, luckily we have natural log, natural log, natural log, and then a common log. So we can use all of our nice, quote-unquote, nice logs. I'm trying to see where on my calculator I have a log. I bring the big O honking calculator, and then I don't even know where a log is because it only gives me ln. I may just use my regular calculator. Okay, so ln, find on your calculator where you have your ln button. You type ln, and then this is 6, 4, 5, 7, 7, 8. You may need to close your parenthesis depending on how your calculator inputs that. And you may have to do like an equivalency button because it's just going to, like if you hit enter and it just tells you ln of what you just typed in, then you're going to have to hit equivalency because it's a decimal. And so I got 13 point blah, 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 blah. If you're using a calculator and it asks you to actually compute it using a calculator, it will give you a specific amount of decimal places that it wants you to round to. So in this case, you get 13.3782. And in actuality, we don't need a calculator for any of the others. We should be able to look at the other three and figure out what they are without a calculator. Now, maybe you can't just yet, and that's okay. But based on that little stack of special rules that we just saw, all the other ones are kind of covered. We have ln of e. Remember, ln means you have log base e of e. If we have log base e of e, then what do we have? Yeah. If these two numbers are the same, it's 1. Now, the next one isn't from our special little rules, but it's from the definition of logarithmic function at the very beginning. For x is greater than 0. Well, where does x fall in our logarithm? That's what we're taking the log of. We cannot take the log, natural, common, or otherwise, of negative numbers. Cannot do it. This does not exist. If you try to type that in your calculator, you're going to get an error. You cannot take the logs of negative numbers. And then the last one, log of 1, that is one of our special rules. The log of 1 is what? And if you don't know, you can type it into your calculator. It is 0. Because this is our common log, right? There's no base written down here, so that means we assume that the base is 10. So 10 to what power is going to give me 1? 0. So that means log of 1 is 0. Now, I mentioned to you just a minute ago that if I was trying to type into my calculator, let's scroll back up here. If I was trying to type into my calculator log base 3 of 7, I can't do that. My calculator does not work that way. I can do log base 10 and I can do log base e. That is it. But there's going to be times when I need to compute what log base 3 of 7 is. And even if I convert that over here to a exponential, it doesn't really help me because I don't know 3 to what power is going to give me 7. Sometimes when I convert over, it helps. Like I can take the cubic of both sides, like the cube root, and figure out some values that b would be, right? I could do that. And up here, I mean, I just compute it. But for this one especially, I have no idea how to go about doing this. And so because of that, we have a nice little change of base formula that allows us the opportunity and the way to type into our calculators these log base other things, like bases that aren't 10 or e. We have a way to type these into our calculator. And the nice thing is we can either use common logs or we can use natural logs, and it's going to give us the same thing. So if you have log base b of m, then we can type that into our calculator by taking the common log of m and dividing that by the common log of b. Or we can take the natural log of m and divide that by the natural log of b. You will get the exact same answer. So the base of the original log goes to the basement of your fraction, if you want to think about it that way. The b is always going to stay in the bottom. Base, basement. Base, basement. But this allows us a way in order to type all these other logarithms into our calculator, so that that one that we were just looking at, if I wanted to type this into my calculator, I could take log of 7 and divide that by log of 3, and that's going to tell me what log base 3 of 7 is, which is pretty cool. So try and leave that change of base up there as well. We're going to use the change of base formula to figure out what log base 5 of 8 is. And we're going to do it both ways so that you see that it does work both ways. For part A, we're going to use the natural logs. Or not, excuse me. We're going to use the common logs. For part B, we're going to use our natural logs. So I have log base 5 of 8. For A, I'm going to use my common logs. So I'm going to have log of 8 over log of 5. Log of 8 over log of 5. And I'm going to type that whole thing in. Oh, I don't know where my log is, though. Algebra? See, when you get like a smarter calculator, then it does too much stuff, and you're like, I don't know what to do with it. Okay, we'll do it this way. So I'm going to use my phone. Log. So you have to type in the 8 first if you're using a calculator. Divide that by, what was it? Log of 5. Does that look like what you guys get? No, of course it doesn't. Because I'm trying to use my phone. Well, I don't know where my log is on my big calculator, guys. Oh, that's fine. There's a smaller calculator over here. Aha, we'll use this one. So it's got a nice little, where'd it go? Top left, there it is. Thank you. Log of 8 divided by log of 5. Get 1.29 blah, 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 blah. Cool beans. That's what I got to. 1.29. How far do I take it in my notes? That doesn't matter. 2920. We'll take it out forward. Now we're going to do the same thing, but we're going to use ln's. So log base 5 of 8 is going to be ln of 8 over ln of 5. On this calculator, it has its own ln button. Sometimes your ln button is part of another button and you have to hit like a second and then that button. It just depends on what your calculator is like. So ln of 8 divided by ln of 5. Notice we get the exact same thing. So it does not matter which way you want to go with it. Obviously, if I was using my big calculator, I would use my natural log because I can't find my regular log. But for most of your calculators, they're nice and right up front. It's 1.2920. Are there any questions on how we use our change of base to change the bases and type them into our calculator? All right, let's convert and solve. We finally have something that says solve. These are the first ones where we're actually going to figure out what these different variables represent. Now, on some of these, like A, it says e to the t equals 70. Remember, e is a number, so don't treat it like a variable. We're not trying to figure out what e and t equals. We're just trying to figure out what t is, okay? And what we're going to do is, if it gives us our exponential like this, we're probably going to have to convert it, because it says to convert it over to a logarithmic form to solve it. So if I'm going from exponential to logarithm, remember I have log, and then I'm going to have the base of my exponential, which is e. The base became the base, and my answer of my log had become my exponent. And what I took the log of became my new answer. The base becomes the base, the answer becomes the exponent. So it does check out. But now log base e, how else do we write that? Yeah, the natural log. So this would be the ln of 70 equals t. Well, I can figure out what the ln of 70 is with my calculator. Ln of 70 tells me that t is approximately, those curly, wavy equal sign, that's not just me having like a hiccup as I write my line. It means approximately, it means I'm rounding. 4.2484. 5. Sorry, if I was rounding correctly, that would be a 5. Because there's a 9 after that 4. So if they give you an exponential and they tell you to convert and solve, then you have to convert it into your logarithm. And then either you're going to have like log base e or log base 10, which tells you a natural or a common log, and you can just type it in. Or you'll have to use your change of base in order to compute out what that variable is. If they give you a logarithm, then you're going to convert it over to your exponential and solve. So log base 5 of 5 equals x. What does that look like in exponential form? Okay. So what does x equal? X equals 1. Because if we look at the 5 on the right-hand side, there's not an exponent, so we can always say that there's an understood 1. And if the bases are the same, you can just look at the exponents. And that's a really nice trick. This is going to happen a lot in the next section when we're trying to actually solve different equations. So x equals 1. Now this one you might look at and say, well, did I need to actually convert it to solve it? And in reality, you don't. If you realize over here on the left-hand side that you have the base and what you're taking the log of are the same, that's one of our special log rules that we learned about, where this is all going to be 1. And so you could do it that way as well, because on your homework, it's not going to ask you to type in this middle part. It's just going to ask you for what x equals. So are there questions on those? Okay. I did copy this page because it was a lot of information. It's a lot of the same information actually from what you had in 5.2. Because logarithmic functions are the inverses of your exponentials. And so on the graphs right here that I include in the middle part of this page, I include the exponential, but then I also include the logarithm so that you can see how they are inverses of each other and how if I folded these graphs along that y equals x line, they would lay right on top of each other. This one's a little bit harder to see because they do overlap, but they really would lay right on top of each other. And so since they are inverses of each other, if you were to look at your notes from 2.5, you would see that the domain and range are flip-flopped. The domain for our logarithm goes from 0 to infinity, and the range goes from negative infinity to positive infinity, whereas for our exponentials, those were the opposite of each other. Now, I did mark a little bit more specifically that obviously if we start doing translations, those do affect some of our domains and things like that. For this one, for our logarithm, we have an x-intercept at 1, 0. Remember, for our exponentials, we had a y-intercept of 0, 1. All we do is switch our x and our y's, and that's how it works. So there's no y-intercept unless there's some sort of a translation. As you can see from the general graph of our exponential, remember we had an asymptote here. If you look at the graph for our logarithm, we're going to have an asymptote on our y-axis. If our base is positive, if it's greater than 1, then we have an increasing function. That's what happens over here. If our base lies between 0 and 1, so it's a fraction, we're going to have a decreasing function. So that's all good information to have. It's because you are going to have to graph some of these. And then I did a table straight out of your books. It's the same table you've seen probably 6 times now, because we've seen it with polynomials, we've seen it with quadratics, we've seen it with our exponentials, and now you're seeing the same thing with your logarithmics. So you've seen it at least 4 times, where it shows the different types of transformations, like your vertical shift, horizontal shift, and all that kind of stuff. And it shows you what the generic form of that would look like, and it tells you what's actually happening in your functions themselves. Now, I told you just a few minutes ago, you can't take the log of a negative number. And that's true. You really can't. Like, computationally, you cannot put that in. But graphically, we can represent what it is, because what that's telling us is we are actually reflecting it about the y-axis. And so we would treat it like it's a positive number, and then we'd flip it over that y-axis to see where it would lie if we were actually able to compute it. Just like with every other transformation that we've done, if it affects your vertical, it's going to be stuck on here at the end. Some books will write that in the front, just so you know. Some books will write this as g of x equals c plus log base b of x, or negative c plus log base b of x. And they do that to try and eliminate confusion between this and log base b of x minus c, where some people could read this and they could read that as a vertical shift, or some people would read it and they would automatically in their minds put parentheses around that, which changes it to a horizontal shift. So just know that if you're looking at your homework, or if you're looking at other references for this kind of stuff, if they stick that C out front, it's still a vertical shift. They're just really trying to draw your attention to the fact that it's not happening inside of the log. Because if it happens inside of the log or inside of the function, then it's horizontal. Does that make sense? Okay. Because you'll see that right here. This is also another point where if you're typing things into a calculator, you definitely want to be really specific. If you noticed when we started typing logs in to this calculator, if I type log, it automatically gives me a set of parentheses. And so if I do log of 4 plus 3 and close it, then that's thinking it's going to do more of a horizontal shift situation. But if what I meant was I want to take the log of 4 and then do a vertical shift up, then I'm going to have to do my parentheses not outside of it like that, but in here. Like that. Where now I'm saying I'm taking log of 4 and I'm going to vertical shift that up 3 units. Okay? So where you put your parentheses, even as you're trying to do some sort of computations in your calculator, is very important. I did note at the bottom that if you do some horizontal shifts, that will affect your domain. And that's because our domain is limited from 0 to infinity for these logarithmics. But if I'm shifting to the left, then my asymptote shifts to the left, which means my domain shifts to the left or to the right, whichever way I'm going. It's no different than when we were shifting our exponentials up and down, and that affected our range from 2.5. Okay, so I just mentioned that horizontal shifting affects the domain. And so some of your questions could just ask you to find the new domain. So for f of x equals log base 4 of x plus 3, the thing I would like to note first is that your starting value for your domain based on that information is is 0 to positive infinity. That's kind of your starting point. That's what the domain looks like if we don't do any type of shifting, is 0 to positive infinity. But for this equation or this function, I have that x plus 3. What kind of a translation is happening there?
To the left 3.
Right, I'm going to the left 3 units, aren't I? So if I go to the left 3 units, that affects my domain, because then instead of starting at 0, where am I going to start at? I'm going to start at negative 3. So my domain then becomes negative 3 to infinity. And again, we don't use brackets, we use parentheses because we're going to have an asymptote there at that negative 3. Because if we're shifting the graph, we're shifting the asymptotes as well. So for g of x, we have the natural log of x minus 5. So what kind of a translation is going on there? We're going to shift to the right 5 units. So what does that do to our domain? That's right. We're moving that whole graph over to the right by 5 units. That includes our asymptote. That includes our domain. Okay, what about our last one? Our h of x equals ln of x plus 7. What kind of transformation is going on here? That's right, that's a vertical shift. There is no set of parentheses around that x plus 7 to tell us that that's happening inside of the log. So we treat it like ln of x and then plus 7. You could also rewrite it as I just showed you, where that 7's out front if you really don't want to get confused on it. So if I do a vertical shift, what does that do to the domain?
0 to positive infinity.
That's right, it doesn't do a dang thing. Our domain stays exactly the same because all we're doing is shifting our graph up and down. But since our graph already covers our whole range, like that doesn't affect anything with our domain at all. And so, good job.